Observations are not permanently committed to a cluster. They're moved when doing so improves the overall solution. However, the use of means implies that all variables must be continuous, and the approach can be severely affected by outliers. Okay, so now I'm going to go into actually running the cluster analysis. So, an organization wants to understand the types of people who are applying to their company. They have a good reason to believe that there are a few different groups of people applying, and they're considering designing their recruitment strategies to better attract certain types of candidates. So my data has employee ID, which that's not going to be an employee, it's going to be applicant, but I forgot to change it because I had to change this data around. These are the variables, let's just say items, and then these are the miles away from the company that a person lives. So I'm first going to attach my data. Actually, I need to import it. I forgot. Frick. And of course it's not showing up now. Okay, great. It's literally right here. There it is. Okay, sorry. I thought that I did this before I started, which I usually do, but I guess I forgot because I just sweep everything out. Okay, anyways, so now I'm gonna attach it. The next thing is to load the rattle function. This actually stands for the R analytic tool to learn easily. And it basically provides a collection of utilities functions for graphing, which we're going to need. The head function is going to return the first rows of a matrix or a data frame. So just so you can see the first couple of rows there. The next part is going to standardize the variables using the function scale. And then the k-means, I'm going to specify a function of 3 clusters here. And then the k-means fit is what I'm calling it, and it's an R object of class k-means. So that's basically me creating the object using the k-means function. Okay, so the next part is the centroids. So this is going to give us a cluster means matrix. It's going to have the cluster numbers from 1 to 3 and then the variables across the top. And then the clustering function is going to give us a vector of integers indicating the cluster to which each point is allocated in the data set. So these are just different ways of looking at your data and all those components that go into the cluster analysis, or actually out of is a better way to say it. And then the k-means fit with the size function is going to tell us how many observations are in each cluster, basically the number of points. So there's 20, 30, and then 50 in 1, 2, and 3. Now we're going to generate the graph to find the optimal value of clusters, which are k. And set seed function sets the number of iterations, like I was talking about earlier, to guarantee that the results are reproducible. So there's that. The next part of the syntax is going to generate the elbow chart. This is similar to what we see in factor analysis when we're trying to determine how many factors to extract. The K-max in the syntax is going to specify the max number of clusters to appear in the chart. Data specifies the data frame. I want the standardized data here, not the original data. The format of the k-means function in R is k-means x centers, and the x is going to be the numeric data set, so the matrix or the data frame. And centers is the number of clusters to extract. N-start is the code for how many random sets should be chosen. This clustering approach can be sensitive to the initial selection of centroids, so the k-means function has this option that attempts multiple initial configurations and reports on the best one. They say that this approach is recommended. The iter max is the maximum number of iterations that you're going to allow. This is something that you specify once again. The tot withins is, total within clusters, sum of squares. I like tot better though. X lab and Y lab. These are the labels for the legend within the graph. We're going to tell the plot function to pull from the objects we just specified in the syntax above. That's basically like what's going on here. So here we see the elbow chart. An elbow chart is going to plot the within group sum of squares versus the number of clusters extracted. So based on this chart, there is a distinct drop in within group sum of squares when moving from 1 to 3 clusters. So after 3 clusters, this decrease drops off, suggesting that a 3-cluster solution may be a good fit for the data. So again, it's kind of like factor analysis where you want to be, I guess, like parsimonious. So it's basically telling us that adding a 4th, 5th, or 6th cluster doesn't add an amount of variance that will make a big enough difference in the variance accounted for within the clusters. Okay. So the next thing is using PCA to cluster the solution into 2 dimensions. So we need the cluster function to do that. And then we're going to generate the plot. The CAD.stand is the object that we created earlier. Main equals the title for the plot using the $$ call function. And then the 2 labels are specified here, and then no lines. Alright, so here is the cluster output. So we do see that a 3-cluster solution works. It accounts for almost 80% of the variance. This is just a very small cluster. There's 3 distinct groups defined by each of these shapes. It takes the k-means results and the original data as arguments into this plot. So the observations are represented by points, using principal components if the number of variables is greater than 2, which it is. The fact that the 3-component solution is best means that the 3 components can explain most of the data, or to be exact, 79.3% of the variance. But we also need to know how well the k-means clustering uncovered the actual structure of the data contained in the type variable that we specified. So a cross-tabulation of cluster membership is going to be given by this syntax. And then we can actually quantify that agreement by, we'll print the output. And then we can actually quantify that agreement between employee and cluster, or should I say applicant, I just never changed it, using an adjusted rank index provided by the FlexClust package. This is the RAN index, and it's on a scale from -1 to 1. So load that in. -1 is going to mean no agreement, and 1 is perfect agreement. So here we have a 0.24. I mean, it's not that great. But yeah, I'm going to go back and maybe fix some stuff, but I wanted to get like some